Hello, everyone, and welcome back to the third part in our little mini series on some more advanced physics. So we're done with relativity. We're done with the large scale stuff of gravity and black holes and planets and whatnot. This time, for one night only, we are going to be diving in to the subatomic realm and talking about particle physics and quantum mechanics, and hopefully a relatively simple and straightforward way to get a grasp on things. Now, we're not just talking about it because it's cool to talk about it, and it is kind of cool to talk about it. But we're talking about particles in the subatomic realm because it does have implications for things we see in astronomy, which we'll talk about towards the end here. So without further ado, I'm very excited about tonight's quote because it's from a great man, Douglas Adams. There's a theory which states that if ever anyone discovers exactly what the universe is for and why it is here, it will instantly disappear and be replaced by something even more bizarre and inexplicable. There's another which states that this has already happened. Of course, that's from his book, The Restaurant at the End of the Universe. All right, before we get into our modern understanding of the subatomic world, let's take a bit of a history trip and talk about how we got to where we are today. So it all started back, of course, with the ancient Greeks, where the word atom actually comes from an ancient Greek word for indivisible. And it was likely the Greek philosopher Democritus, which you see pictured there on the right. He's smiling. He was known as the laughing philosopher, the smiling philosopher. So all of the paintings of him have him usually laughing at something. But he was the first one to conceptualize the idea of something very small that makes up everything. But where he differs from our modern point of view is that he imagined different types of atoms for different substances. So, for example, iron atoms have little hooks which lock them together, which is why iron is solid at room temperature. Meanwhile, water atoms are smooth and slippery, which is why water is a liquid at room temperature. Obviously, this is not at all how we think about atoms today, as we'll see. But it was a good first step. And this idea lasted until the scientific revolution, until the 13, 14, 1500s in Europe. Once again, not because people were stupid and just believed that there were tiny little balls rolling around with hooks on them to make iron a solid or whatever. It's just this theory worked to explain things until the scientific revolution. They didn't need to have a deeper understanding to go on with their lives. But eventually, we did get around to getting that deeper understanding. And the first person to do that was John Dalton, an English chemist in 1803, where he still took what Democritus had and said that atoms were these small, hard spheres that are indivisible. They cannot be broken down any further. And that the atoms of a given element are the same. And that second point is actually true. Every gold atom is the same as every other gold atom. Every oxygen atom is the same as every other oxygen atom, except for the important distinction of isotopes. Remember, we talked about isotopes a long, long time ago. We can go back to some of the earlier talks on, I think, matter, energy, and motion towards the beginning. But remember, isotopes are atoms that differ in the number of neutrons. It's the number of protons that determine what an element is. So, for example, oxygen has 8 protons, carbon has 6 protons. But if you change the number of neutrons, you get a different isotope. So carbon-12 has 6 protons and 6 neutrons, but carbon-13 has 6 protons and 7 neutrons. It's still the same element, just slightly different. So we call it an isotope. So he didn't know about those. But he was true that every atom of any element is essentially the same thing. It's indistinguishable from each other. He also was the first person to come up with ideas on how atoms can join together to form compounds. So we all know water, H2O, is 2 hydrogen atoms joined to an oxygen atom. He was the first person to figure out a way of how they could do that. And he came up with the first symbols for the chemical elements, way different from our periodic table you see down there at the bottom. He only created 36 symbols. You see carbon is just a filled-in gray square. Hydrogen is a circle with a dot in the middle. Some of them just have letters in the middle, lead instead of PB on our current periodic table. He just put L up in a circle. So these were once again, a good first step towards our modern understanding of atoms. And his idea of how atoms worked and how they joined together to create chemical compounds held sway for a little less than a century, until J.J. Thomson discovered that the atom isn't indivisible like everyone thought. The way he did this was he performed experiments using a cathode ray tube. And yes, that is the same cathode ray tube that puts the CRT in CRT TV. So cathode ray tubes fire out a stream of charged particles. And what he did is he put two charged metal plates, one positively charged, one negatively charged. And as he shot these charged particles out of the cathode ray tube, passing between the two charged metal plates, the charged particles coming out of the cathode ray tube were pulled towards the positively charged metal plate. So this allowed him to deduce that the rays themselves must be negatively charged. He was also able to deduce, through some math I'm not going to get into, that those rays are made of particles 2,000 times lighter than the lightest element, hydrogen. What J.J. Thomson had in fact discovered was the electron. And that actually won him the Nobel Prize in 1906. It was so easy to win a Nobel Prize in the early days. But that suddenly, atoms weren't indivisible. There was a part of them that had a negatively charged part. There's a part of it that has a positively charged part. Suddenly there were parts to atoms, and this was quite revolutionary. One of Thomson's students took it a step further. His name was Ernest Rutherford, and he provided some further insights into the internal structure of the atom. So Rutherford, in his experiment, he had essentially a radioactive source that was going to be constantly emitting some charged particles. He called these particles alpha particles. That's still a term we use today, although we now know that alpha particles are in fact just helium atoms, helium nuclei. And he was going to cause these alpha particles, these helium nuclei, to be fired at some gold foil. And he would put a fluorescent screen around the gold foil to see where these charged particles ended up after passing through the gold foil. And most of them did pass through. You could see them on the exact opposite side of the gold foil. Here, this darker red spot passed straight through. But a few of them were scattered away in weird angles, coming just to the side of where most of them were, to going almost backwards. It was as if you were firing a bullet at a piece of aluminum foil, and the bullet ricocheted back and hit you. This was incredibly weird. Excuse me. The only way that this could happen was if the positive charge of the alpha particles was concentrated in a small, dense region. In other words, the nucleus. And so Ernest Rutherford built off of his professor's ideas, J.J. Thomson's ideas, and made the first atomic model, where we've got a positively charged hard ball nucleus that's indivisible, with some negatively charged electrons kind of floating randomly around that positively charged nucleus. And this was sort of the atomic model for a few years. That is, until Niels Bohr. Because one problem with this model, if we go back here, we know, even though we haven't really talked about electricity and magnetism as much, we're more concerned with mechanics throughout this series, we know intuitively that negatively charged things and positively charged things attract. They want to come towards each other. Like charges repel, opposite charges attract. So the big question on everyone's mind is, why are electrons just hanging out? Should they not just automatically fall into the nucleus? Shouldn't matter then not be at all possible if this is the correct model? Well, it came down to the Danish physicist Niels Bohr. He was around at the very beginning of quantum mechanics, of quantum theory, coming to explain the subatomic world. And so he was the first person to use what was then known about quantum theory to explain the arrangement of electrons. And he's possibly the thing that we've already talked about several weeks ago. where he said that there are energy levels in an atom, energy levels surrounding the nucleus, where and electrons could only be found in those specific energy levels. So they could be at 0 or 1, but not a half. There's no such thing there. In other words, this energy is quantized and couldn't take any random value. It's not a smooth distribution. It's very discrete. And so this model didn't really get everything right, but those problems would be realized for another few years. And this is still a very useful model. In fact, even though this model is incorrect, it's still a model that high school chemist students and chemistry majors in college use to think about how atoms bond together to form compounds, where instead, in the nucleus, instead of just one solid, unbreakable, positively charged ball, we've now got several of those, the protons, colored here in red, the neutrally charged neutrons, they don't have an electric charge, and then the energy levels of electrons orbiting the nucleus. The neutrons were discovered between Rutherford and Niels Bohr. So this is a really good idea of what an atom is. It has some problems, and we'll talk about that as we go on. But this is a really good idea, a really good picture to have in your head of what an atom is. And so I want to talk about the basic properties of these subatomic particles, because there are really only 3 properties of particles: mass, electric charge, and spin. So mass, we know what mass is. Here, the only thing that's different is what units we're talking about when we talk about a particle's mass. Of course, we can express a particle's mass in solar masses or kilograms or Earth masses or whatever. Even grams is still too big. You see, I've put the numbers here for the masses of the proton, the neutron, and the electron. These are really, really small masses in grams, 10 to the minus 24, 10 to the minus 28. We can also talk about masses in terms of atomic mass units. Now, I do have to make the distinction here. I am using the unified atomic mass units. For some god-awful reason, physicists and chemists have completely different definitions of what an atomic mass unit is. And so thankfully, they've unified them now. So what I'm talking about here is the unified atomic mass units. Where you see a proton is 1.007, neutron is 1.009, electron way less massive, 0.0005. But thanks to Einstein and his equation E equals mc squared, energy is mass times the speed of light squared. We can also express these masses in terms of energy. Typically, we'll talk about them in terms of mega or giga electron volts per c squared, per the speed of light squared. So you can see on the rightmost column in this table, their masses in mega electron volts per speed of light squared. So proton about 938, neutron about 939, electron just over a half of a mega electron volt per c squared. For those of you who are curious, an electron volt is the energy that an electron has when it's accelerating from rest through an electric potential of 1 volt. It's an incredibly small amount of energy. In terms of the normal SI units of joules, 10 to the minus 19 joules. So this is way more useful to talking about the subatomic than talking about masses in grams. So atomic mass units, mega electron volts per c squared. Those are the units of mass talked about in particle physics. When it comes to electric charge, you can either talk about a charge in terms of the SI unit of coulombs or the elementary charge, E, which is the charge of a proton or an electron. So remember that charge can be positive, negative, or neutral. So a proton is positively charged, neutron is neutral, has no charge, and electron is negatively charged. And you can see the charge there in coulombs in the middle column. Once again, really small numbers, 10 to the minus 19 for protons and electrons. Or what is way more common, just talking about in terms of the fundamental charge, the elementary charge. Proton has a charge of 1, neutron a charge of 0, electron a charge of -1. That's how we'll talk about charges from here on out. And then finally, that last property, spin. Spin is a difficult one to get across. Spin is essentially shorthand for the particle's spin angular momentum. So just like a spinning ice skater or a spinning ball has some angular momentum, particles have their own intrinsic angular momentum. But it's very important that particles are not actually spinning like balls. In fact, we think electrons don't have any size to them. They're just a single like mathematical point. So it's not really a surface that is spinning around an axis or anything like a basketball is, or like the Earth. This is just a property that inherently belongs to the particle, and it can't change. It's quantized. So spin can be written in units of the SI units, Newton meter second, or as a dimensionless quantity, which is what particle physicists usually do. Planck's constant, h, just another constant, just like the speed of light, or Newton's gravitational constant, divided by 2 pi. We generally call this h bar. That's how it's written. So, and spin can come in either integer values or half integers, where those particles with the half integer spins can be called either spin up or spin down, which essentially correspond to the two opposite senses of rotation. So you can see the spins for protons, neutrons, and electrons in that table. We will not talk about the Newton meter second part because, once again, it's very small numbers, 10 to the minus 35. But you can see they all have a dimensionless spin of plus or minus 1/2. They can be spin up with 1/2 or spin down with 1/2. That's essentially what that's saying there. So that's really the only fundamental properties of particles: their mass, their electric charge, and their spin. That's it. That's all there is to particles. However, in the 1960s, scientists, physicists have discovered dozens of different particles, each with a unique set of properties. You can see several of them here. This is what Murray Gell-Mann, a physicist, very famous physicist, he only died in 2019, and that was a big loss for the physics community. It's like losing access to the Encyclopedia Britannica. He's very, very smart. Back in the 60s, he came up with this way of arranging these different subatomic particles. This is called the Eightfold Way, after a similar thing in Buddhism, which he was sort of into for a bit. And this is very confusing, tons of different particles, but let's just talk about the hexagon in the middle. So you see these different quantities, S's and Q's. The S stands for strangeness, a particle's strangeness, which is a legitimate quantity particles have. The Q, for whatever reason, stands for electric charge. No idea why we use Q to call electric charge. But the way to read this is, here we've got N for neutron, P for proton. If we go down here, we see that protons and this other particle called a sigma particle, positively charged sigma particle, both have an electric charge of 1. Similarly, following this route, the neutron, neutral sigma, lambda, the neutral psi have an electric charge of 0. And going down this way, the negatively charged sigma, the negatively charged psi has a charge of -1. We also go the other way towards the strangeness. So protons and neutrons have a strangeness of 0. The sigma particles and the lambda have a strangeness of -1. And the psi particles have a strangeness of -2. We're not going to get into what strangeness is. But this is a way of organizing all of these particles together in a way that hopefully made sense to physicists. And this is actually very useful because I'll point out one particular particle, and that is this particle right there at the tip of that triangle, the omega minus. That particle did not exist when Murray Gell-Mann came up with the Eightfold Way. But he knew that some particle had to be here at this vertex to have a charge of -1 and a strangeness of -3 to fill out the rest of this triangle. And later, they did actually go and discover the omega minus particle. I show you all this, hopefully not to confuse you. But this was a sort of a beginning step to what we now call the Standard Model. The Standard Model is way more simplified than those weird hexagons and triangles, with only a few subatomic particles here. We've got the quarks colored in purple, the leptons colored in green, and then the bosons. There are 2 types of bosons. We're not really going to distinguish the 2 types, but the gauge bosons in red and the scalar bosons in yellow. We're going to break this down, but this is essentially our current understanding of particle physics, all written here in this nice little diagram. So let's break this down. So the most fundamental distinction between particle types depends on spin. Particles with half integer spins are called fermions, named after Enrico Fermi. And particles with integer spins are bosons, named after Satyendra Bose, an Indian physicist. So half integer spins, plus or minus 1/2, plus or minus 3/2, those are fermions. Integer spins, plus or minus 1, plus or minus 2, those are bosons. The fermions are then also subdivided into categories, the quarks and the leptons on the standard model. Both quarks and leptons are truly fundamental and cannot be divided further. Quarks interact with each other via the difference between quarks and leptons is that quarks interact with each other via the strong nuclear force, which we'll talk about in a minute, and leptons don't. Quarks are also never seen by themselves in nature, but leptons are. So for example, protons, neutrons, and electrons are fermions, because remember, their spins can be plus or minus 1/2. But photons are bosons, because their spins can only be plus or minus 1. And for example, protons are made up of quarks, and neutrons are made up of quarks, while electrons are leptons, and they are truly fundamental. So protons and neutrons, not fundamental. You can continue to break them down into their constituent quarks. Meanwhile, electrons are fundamental. There's nothing inside of an electron. So just like I said, protons and neutrons are made up of quarks. They are both made up of up quarks, which has an electric charge of positive 2/3, and down quarks, which has an electric charge of minus 1/3. So proton is 2 ups and a down, and neutron is 1 up and 2 downs. And just as a proof of concept, if you add up the charges, so a proton, we know a proton has an electric charge of +1. That means those quarks got to add up +1. So we've got 2 up, so 2/3 plus 2/3 is 4/3. And a down, add a negative 1/3, and you get 3/3 or 1. Similarly, for a neutron, an up is positive 2/3, add a negative 1/3 and a negative 1/3, so you get 0. Neutrons are neutral. We're not really going to distinguish between mesons and baryons, but if you hear those terms, know that there are some particles that are made up of 3 quarks, like the protons and the neutrons. These are called baryons. We'll talk a little bit more. You'll hear that term again when we talk about cosmology towards the end of this whole series of lectures. And then you also make up particles of just 2 quarks, and those are called mesons. For all intents and purposes, we're not going to really distinguish between the two. And so you can see there are more than just the up and the down quarks. The up and the down quarks are the lightest quarks. They have the least amount of mass. But there are 2 more generations of quarks. We have the charm and the strange, and the top and the bottom quarks. And those, you can combine these 6 quarks into many different weird and esoteric particles that we never see in our daily lives, that only exist for split seconds in the most chaotic, high energy environments imaginable. Probably, early on in the Big Bang, maybe in some, maybe near black holes, very chaotic environments, but you'll never, receive a piece of paper made up of particles that are made up of strange and top and bottom quarks and charm quarks. Everything we deal with is made up of up and down quarks. The leptons, the electron is the only type of lepton that we see every day in ordinary matter. But there are, just like quarks, there are 6 total types of leptons. There are 3 electron-type leptons, the electron, the muon, and the tau. Think of the muon and the tau as just progressively heavier versions of the electron. While and then there are 3 neutrino types electron. There are 3 neutrino type leptons: the electron neutrino, the mu neutrino, and the tau neutrino. Neutrinos, although we certainly know about them, they don't interact with matter hardly at all. Neutrinos can pass through a light year of lead before hitting a single lead atom. They don't interact with matter at all, even though we see them all the time. In fact, if you look at your hand right now, there are about 1 trillion neutrinos passing through your hand. every second. But we don't really worry about them. Now, in truth, the standard model should be about twice as big, because every quark and lepton has a corresponding antiquark and anti-lepton, which are completely identical except in opposite charge. So, for example, an up quark has a charge of positive 2/3, but an anti-up quark has a charge of minus 2/3. Just like an anti-electron has a charge of positive 1, while an electron has a charge of negative 1. Antimatter is essentially the same as our own normal matter, except for that opposite electric charge. And when a particle and its corresponding antiparticle meet, that's going to be a bad day for those particles because the result is complete annihilation. They meet, and immediately their combined mass turns into energy via E equals mc squared. Now, as you might notice, that doesn't happen around our normal everyday lives that often, because the universe is primary matter. Antimatter is created inside some stars. It is created, but it is always almost immediately meets up with a normal matter counterpart and annihilates. Why our universe is just matter instead of an equal parts matter and antimatter? That's weird. We have no idea. That is a question for the ages. There are people working really hard on that weirdness there. But we're very thankful that we are a primarily matter universe. This process also works in reverse, and this will come into play towards the end, where energy can randomly turn into a particle-antiparticle pair. And this is known as pair production. This happens inside particle accelerators, inside stars. It happens all over the place. In fact, during the first few moments of the Big Bang, which is why we have particles in the first place, because of this pair production. So antimatter is real. It's not just something from Star Trek. And then let's talk about those bosons. Those bosons represent 3 of the 4 fundamental forces. The 4 fundamental forces are gravity, which we've talked a lot about these past 2 weeks, electromagnetism, the strong nuclear force, and the weak nuclear force. Now, first of all, gravity does not have its own particle, because as we talked about last week, gravity is caused by the curvature and bending of space-time, not by an actual particle. But the other forces have their own particles. And you can see them there. The strong nuclear force is mediated by the gluon. The electromagnetism is mediated by the photon. And then the weak nuclear force has actually 2 particles to it, the Z and W bosons. Both of the nuclear forces, the strong and the weak one, only work within atomic nuclei. Remember, a nucleus has a bunch of positively charged protons all stuck together. And if electromagnetism were the only force that worked down there, the nuclei would certainly not stay together. Remember, like charges repel. And so we have to rely on the strong nuclear force overpowering electromagnetism, keeping those positively charged protons stuck together in the nucleus. The weak nuclear force allows nuclear reactions to happen. Remember, we're talking about fission, nuclear fission. That is primarily the weak force working there. Each of those, just like I mentioned, is transmitted by an exchange particle. That's the technical term. That transfers momentum between 2 interacting particles. In the universe, electromagnetism is the strongest force by far, way stronger than gravity. This is sometimes surprising to people to hear that electromagnetism is stronger than gravity. But when you think about it, you already know it. If gravity was stronger than electromagnetism, then you'd never be able to stick magnets on your fridge. If people still do that. It's only because electromagnetism is stronger than gravity. And so it governs every aspect of chemistry and biology. Everything in chemistry and biology can essentially be boiled down to an electromagnetic reaction, electromagnetic force working. Gravity, in fact, is the weakest force in the universe. But it governs planets and stars and galaxy and us because the nuclear forces are way too weak on large scales, and most objects are are electrically neutral. I can't just throw this book up on my fridge, or a mask or my phone up on a fridge. They're all electrically neutral. So that's why gravity seems to dominate at these moderate and large scales, while in fact electromagnetism is the strongest force. All right. So that's an introduction to particle physics. There's some wonderful websites and wonderful books that break down particle physics at a very simple level. So definitely go search those out if this is as interesting to you as it is to me. I really love particle physics. Before I became an astronomer, one of the decisions I had to make was, do I want to study the really small stuff or the really big stuff? Because it's very, very fun to study the really small stuff. A lot more math though. All right, so now let's get into quantum mechanics. What laws of nature govern the particles in particle physics? Well, there are two big ones, and the first one is Werner Heisenberg's uncertainty principle, which states the more we know about a particle's location, the less we can know about its momentum. And conversely, the more we know about its momentum, the less we can know about its location. So this seems really, really weird. Let's break it down here. So if we want to detect an electron, if we want to know exactly where it is, then we've got to have it scatter some photons, because that's how we see anything. Remember, we talked about this in the light lecture many, many weeks ago. I can only see my desk or see my computer because light is bouncing off the computer and entering my eyeball. So similarly, light or a photon has to bounce off the electron and enter our detector. But our precision to locate electrons depends on the wavelength of light we use. So for example, if we used visible light with a wavelength of about 500 nanometers, then we can only measure the electron's position only within 500 nanometers, which is horrible for small stuff because that's about 5,000 times the size of an atom. That is, if we see a flash of 500 nanometer light from a row of 5,000 atoms, we will not know which atom emitted that flash of light. That has to do with our resolution here on this scale. So if we want to locate the electron more precisely, we've got to use shorter and shorter wavelength light. So instead of visible light, let's switch to UV or X-rays. But that starts to create a problem with tracking the electron's momentum, because each photon's energy delivers a little kick to the electron, which actually changes the momentum we're trying to measure. So it's almost as nature we're playing a perverse trick on us. Locating the electron precisely requires hitting it with a short wavelength photon, but the high energy of that photon prevents us from determining the electron's momentum. Conversely, measuring the electron's momentum requires hitting it with a low energy photon that won't disturb it as much, won't give it as much of a kick. But because low energy light has long wavelengths, we won't actually have a very good idea of where the electron is. And what's more is that this uncertainty principle applies to all particles, not just electrons, but to macroscopic objects as well. So if we want to look at a baseball with visible light, then visible light, that's about a 500 nanometer wavelength, we'll only be able to locate any part of that baseball within 500 nanometers. Now, 500 nanometers is a tiny fraction of an inch. So that really doesn't matter if I'm holding a baseball in my hand. I'll know where the baseball is because that uncertainty is so small as to be completely negligible. So that's why Newton's laws work perfectly fine on this larger scale. But it is truly the uncertainty principle that governs our ability to see and measure things on all scales. And this brings us into this whole, can we measure the electron's location or momentum, brings us into stuff that I've talked about a little bit before, the wave-particle duality of particles. The uncertainty principle implies that the electron doesn't even have a precise path. Really, it's more smeared out over a volume of space. This smearing out is at essence what the wave-particle duality is all about. So if we choose to regard the electron as a particle, it's a single point, I can see it, we can locate it precisely. But we have absolutely no idea if we're trying to look at it between 2 points. We have no idea how it is moving between 2 points. It could be going a straight line, could be doing this, could be going backwards and around the other side of the world to that point. We have no idea. What instead we can do is we can talk about a probability distribution of where the electron most likely is. So this is why Ernest Rutherford's, Niels Bohr's idea of what an atom looks like is wrong, where we've got the electrons orbiting in those nice little circular orbits, those energy levels. We don't actually know where the electron is. So instead, what we have here, these are the energy levels for hydrogen, where instead of a precise position, we get these smeared out. Now, the lowest energy levels, yeah, they're going to be in a circular orbit around the nucleus there at the center. But you can see at higher and higher energy levels, electrons are going to be in these, more likely to be in these weird kind of flower shape, or these lobes here, instead of in just a simple circular orbit around the nucleus. So that's why Niels Bohr's atomic model is actually incorrect, but it gets us to where we need to do in chemistry. For physicists, however, they've got to have a handle on wave functions and probability of distributions and all this weird, complicated math. You can see up there at the top, that's just a bunch of horrible math and that I don't want to talk about. Now, on the opposite hand, if instead of talking about the electron as a particle, we're talking about the electron as a wave, then we're able to measure the momentum. We know the speed and direction that a wave is going. But a wave also doesn't have a precise location. You drop a pebble in a pond, and there's going to be a ripple coming out. But you cannot point to any spot along that ripple and say, that part is the wave. All of that is the wave. So therefore, there's not a precise location for that wave. But we can at least measure its momentum. So this uncertainty principle underlies, which is why we talk about particles as this wave-particle duality. We'll keep calling them particles, but know that they have properties of waves as well. So just like light, we usually talk about in waves, where it has a wavelength and an energy. Light is also a particle, the photon. Electrons, we usually talk about them as particles, but they also have like a wavelength because they could sometimes act like a wave. And it's very, very weird. The guy who discovered this name, I forget his first name, but his last name is de Broglie. He wrote his thesis on the wave-particle duality of electrons. And I'm not kidding you, his thesis is like a page and a half long. I long for the days where theses could be just a page and a half of, yeah, duh, this is it. I wish. The second big principle that governs quantum mechanics is Wolfgang Pauli's exclusion principle. So particles are described by their quantum state. So scientists use the term state to describe the current conditions of an object. So for example, if you're relaxing in a chair, a scientist might say you're in a state of rest. But a more precise description of your state in the chair might be something like your current state is a velocity of 0, a heart rate of 65 beats per minute, a breathing rate of 12 breaths per minute, a body temperature of 37 degrees Celsius, a metabolic rate of 200 calories per hour, and so on. You can see it gets very complicated. Fortunately, it's much, much easier to talk about a particle's quantum state, where all we really have to do is specify its location, its momentum, its orbital angular momentum, and its spin. And each of these property is quantized, meaning it can only take on particular values and not any values in between. So once again, remember, quantized is like 0 and 1, but not a half. And so Pauli's exclusion principle states that two fermions of the same type cannot occupy the same quantum state at the same time. So note that this explicitly only says fermions. So remember, electrons, protons, neutrons, but not the bosons, the photons, the gluons, the W and Z bosons. Those don't have to worry about Pauli's exclusion principle. One of the most important consequences of the exclusion principle is it dictates how electrons are arranged around atoms. So an electron in the lowest energy level, which you can see here, colored in magenta, labeled 2 or K, has a particular amount of orbital angular momentum and a very restricted range of locations. The only thing that isn't decided by where the electron is in its energy levels is its own like intrinsic spin. And remember, electrons can have positive 1/2 up spin or negative 1/2 down spin. So that means in the lowest energy level, there can only be 2 electrons. Because if you add a third, it's going to necessarily have all of the same quantum properties as one of the other 2. So that means that there has to be another electron shell. And that outer electron level, that outer energy level, can have 8 electrons in it, the L level. Next one have 18, next one have 32. And this is how chemists think about electrons and chemical reactions and whatnot. This is a very good model for this. Essentially, together, the uncertainty principle and the exclusion principle determine how everything is built, the sizes of atoms, how everything is made out of atoms. The uncertainty principle ensures that electrons cannot be packed into infinitesimally tiny spaces. So if you try to combine an electron into 2 small spaces in an atom, the uncertainty principle tells us that its momentum would then be way too large, so large that the electromagnetic attraction of the nucleus would no longer hold it in the atom. The exclusion principle ensures that each electron has to have its own space. Together, these 2 fundamental laws of quantum mechanics explain why, even though atoms are mostly empty space, everything around us is solid. In the words of the physicist Richard Feynman, he said, "It is the fact that electrons cannot get on top of each other that makes tables and everything else solid." Now, this is all fun and cool. I love talking about particles. Quantum mechanics is very interesting, although somewhat confusing at times. But we're not just talking about it because it's cool. We're talking about this stuff because it does actually have implications in astronomy. It does govern how things work. So the first implication are stars. So in our everyday lives, thermal pressure plays an unexpected role. So for example, if you blow up a balloon and then heat it up, the gas inside of the balloon, the air inside the balloon, will start to move around more rapidly and exert a pressure on the inside of the balloon, causing the balloon to expand without having to add any more air into it. Similarly, if you blow up a balloon and stick it in the freezer, the air inside the balloon will start to slow down and exert less of a pressure on the inside of the balloon, and so the balloon will shrink. You can do that experiment at home. You don't have to just take my word for it. But now, instead of normal air, let's consider what happens if we compress a plasma. Remember, a plasma is a mixture of positively charged ions and some free electrons, electrons not attached to an atom. So first, the energy we expend in compressing the plasma makes the electrons and protons move faster, increasing the pressure and temperature. And so it's going to get very hard for us to keep pressing on it. So let's back off and let the plasma cool a bit. And so the pressure will drop, enabling us to compress it even further. And repeating this process will let us compress the plasma to a very, very dense state. But at some point, the exclusion principle will come into play. The electrons can't all get on top of each other at once. So there comes this pressure that we can't overcome. And this is called degeneracy pressure. Now, where degeneracy pressure comes in is in 2 different forms. Electron degeneracy pressure, where electrons can't sit on top of each other anymore. This affects the lives of stars in several ways. So, for example, it can prevent a collapsing cloud of gas from becoming a star in the first place, creating a brown dwarf. An artist's rendition is in the top right. This is, a failed star. People keep calling Jupiter a failed star. It's not. It's a very successful planet. Brown dwarf is actually a failed star. In stars like the sun, it determines how they begin burning helium towards the end of their lives. When stars die, most stars leave behind an extremely dense stellar corpse called a white dwarf, which is supported by electron degeneracy pressure. You see an artist's rendition of a white dwarf, the center right. However, electron degeneracy pressure does have a limit. And when that limit is reached, the star will continue to collapse until neutron degeneracy pressure takes over. And when that happens, we get a neutron star, which is at the bottom picture. But even neutron degeneracy pressure cannot grow infinitely strong. It cannot continue to support under more and more mass. When that fails, nothing will stop the collapse and we get a black hole. We'll talk about all of this in the coming weeks. But you can see the implications that the uncertainty principle, the exclusion principle, I apologize, plays here when we're talking about the lifetimes of stars. We also have something called quantum tunneling, which you see in the GIF right there. Since the uncertainty principle prevents us from knowing an electron's precise location, if it were bouncing off a wall, you can imagine the ghostly white on the left as the probability of where an electron is. And it's going to bounce off this wall. There is because we don't actually know where the electron is, despite that wall there stopping most electrons, there's a small chance that the electron could be on the opposite side of the wall, essentially tunneling through the wall. This is why we call it quantum tunneling. You see the ghostly white here come out from the wall. So there is a small chance that there are electrons on the other side of the wall. Most electronic devices rely on quantum tunneling. But even more important to life on Earth is that nuclear reactions that power the sun work because two positively charged protons come together. Now, once again, if electromagnetism were the only force at play, then those things would repel and we would never get fusion. Stars wouldn't be a thing. Life on Earth would not exist. But because there's some small probability that even though they're going to repel, that the proton could find itself very close to the other proton, that allows it to overcome that electromagnetic repulsion and allow a strong force to take hold and bind the two protons together. So without quantum tunneling, life would not exist on Earth. This happens not too frequently, but there's also tons and tons of protons in the sun. So the net overall effect is that this happens a lot in the sun. And we've seen quantum tunneling in laboratories here on Earth. We have experimental evidence that quantum tunneling does exist. And finally, not finally actually, empty space. Empty space is not actually empty. According to the uncertainty principle, particles can pop into existence from nowhere. Their mass comes from stolen energy, theoretically breaking the law of conservation of energy. But where it doesn't break the law of conservation of energy is that they pop back out of existence before anyone can verify that they ever existed. So you can imagine that the law of conservation of energy is enforced by a great cosmic accountant. And imagine that the cosmic accountant keeps a storehouse of energy in a large bank vault and ensures that anytime something borrows some energy, it returns the energy in a precisely equal amount. A particle that pops into existence is like a bank robber who steals some energy from the vault. Now, if the cosmic accountant catches the particle holding its stolen energy, someone will have to pay for the theft. However, the particle won't be caught as long as it pops back out of existence quickly enough, returning the stolen energy before the cosmic accountant notices that anything was ever missing. The length of time the particle has in which to pop back out of existence and return the stolen energy is a time short enough that the uncertainty principle prevents anyone from knowing that the energy was missing. And these particles are called virtual particles. And modern theories of the universe propose that space is actually just bubbling with virtual particles popping in and out of existence. And the combined energy of all the virtual particles in the universe is sometimes called the vacuum energy or the 0 point energy. And some theories about our universe suggest that vacuum energy can actually act in opposition to gravity, expanding the universe. Although those theories that rely on vacuum energy to do the expansion at a rate far greater than what is actually observed in our universe. So there's still some mystery there. People are still working on it. So virtual particles are very weird, but they come into play here with black holes. So virtual particles are thought to limit the lifetimes of black holes. So we understand why by extending our cosmic accountant analogy to the case of a virtual electron popping into existence near a black hole. Because electric charge must be conserved, the virtual electron cannot pop into existence by itself. Instead, it must be accompanied by a virtual positron, an anti-electron, so that the total electric charge of the two particles is zero. And like all virtual particles, the virtual electron-positron pair essentially comes into existence with stolen energy. So to remain undetected, the two particles must return the stolen energy before our imaginary cosmic accountant catches them. And they return the energy by quickly annihilating each other. So here we've got an electron and a positron popping in for just a split second. They are immediately going to have to return the energy they used to pop into existence. So they're going to come together, they're going to annihilate, and we won't see either of them. However, let's suppose a virtual electron-positron pair pops into existence very close to, but outside of, the event horizon of a black hole. So here we've got our black hole. And here we've got our electron-positron pair. Now, the electron and positron are supposed to annihilate each other quickly, but a problem arises. One of the particles crosses the event horizon during its brief virtual existence. So one of them goes into the black hole, never to be seen again. Meanwhile, the other one goes off and does whatever it does. From the perspective of our cosmic accountant, this virtual particle was never accounted for in the first place. So there's no problem with the fact that it will never be seen again. The purple particle that went into the black hole, it is. But the other particle is suddenly caught like a deer in the headlights. Without its virtual mate, it has no way to annihilate itself and is caught red-handed by the cosmic accountant. Because the particle is now holding real rather than virtual energy, the cosmic accountant demands that someone or something pay for the stolen energy. The particle itself can't pay because it now has the energy by virtue of its existence. It has no way of giving it back once its virtual partner is gone. The cosmic accountant therefore makes the black hole pay for the energy by giving up a little bit of its gravitational potential energy, thus shrinking it, causing it to evaporate. That's why this is known as Hawking radiation, because this whole idea was first proposed in the 70s by Stephen Hawking. And this idea that black holes can evaporate remains untested. But if it is true, it may have profound implications for both the origin and the fate of the universe. So, for example, some scientists think that black holes of all sizes might have been created during the Big Bang. If that's true, then some of the smaller black holes should be evaporating by now, which emitting bursts of gamma rays that we should be able to detect during their final moments of existence. At the other end of time, if the universe continues to expand forever, then black holes may be the last large masses left after all the stars have come and gone. In that case, the slow evaporation caused by Hawking radiation will mean that even black holes cannot last forever, and the universe will contain nothing but a fog of photons and subatomic particles, separated from one another by incredible distances as the universe continues to grow in size. So hopefully I gave you a bit of a taste for particle physics and quantum mechanics. I will, of course, reiterate some of this stuff as we start talking about stars and galaxies and cosmology. But definitely, if you're interested in this, there are tons and tons of websites, tons of books that go into it at a much lower level of detail than even what I've talked about today. So definitely go pick that out. But otherwise, I will see you guys next week when we finally start talking about the sun and other stars. So without further ado, I will see you next week.